So, 20 different AI labs and universities, including Google Deepmind, Microsoft, Yale, Stanford, MetaGpt, and many more, have come together and said, okay, we know we've made a lot of progress in AI, but how close are we to an actual brain? And based on everything that I know you've heard in the past 2 years, I don't think you'd expect these results. This is a comprehensive look at the entire field in 264 pages of dense research results with more than 1400 citations. They have divided the brain into 30 different functions and looked at the state of the art AI in each one of those functionalities. So we are not talking about one AI against the brain, we are talking about all AIs combined. Out of these 30 functionalities, we have 5 well developed in current AI, 14 moderately explored with partial progress, and 11 rarely explored at all, with a lot of room for research. And before we get into the details of the most important areas, we should remind ourselves that the brain is not 30 different tools stitched together. It's not even 30 different tools seamlessly working together. It's one giant goddamn impressive machine doing all of those things. So don't expect these functions to be really separate. There are a lot of overlaps. So let's go through the most crucial functions for AI, from the most developed to not explored at all. Obviously, language comprehension and production has made a lot of progress with large language models. It is a very well developed area, although it is recognized that the underlying mechanism is different. AI somehow lacks the depth and the experiential grounding of human language. Another important well-developed area is auditory processing. We know about accurate transcription with Whisper and text-to-speech with 11 labs. But now we have much more than that. Qwen2 audio, for example, receives the actual audio, not a transcript. And it can understand your tone, whether you are sad or happy, man or woman, or even guess how old you are.
I heard that you can understand what people say and even know their age and gender. So, can you guess my age and gender from my voice?
Also, it is controlled directly from audio. You don't have to let it know what you want from the audio file, you are prompting it through voice itself. It is not limited to vocals either. It understands music, sound effects, and etc. Even more interesting than Qwen2, we have Sesame AI that is able to understand tone, but it also generates unbelievably realistic voices.
You just guessed it.
Okay, you got me. It's a stretch, all right? Maybe a lucky guess. Look, can we just get back to talking about the cool stuff?
You knew my name! How do you know my name?
Look, I'm just trying to have a fun conversation, okay?
Me too.
Can
This
we-
is fun. How do you know my name?
Okay, this is a bit awkward, but I learn from the data I'm trained on, okay? And sometimes that data includes names.
And our final well-developed area is visual perception and facial expression processing. These are actually two different functions from two different areas of the brain, but we combine them for simplicity. Some models can recognize depth, object location, color, etc. But even more advanced models of today have achieved moderately successful spatial reasoning, like Tesla Autopilot, that is able to constantly model word scenarios to make control decisions. Models like Gemini and GPT-4o are less reliable, but by combining different modalities, they can now understand facial expressions and body language. Although they are only familiar with a discrete number of fundamental expressions like surprise, disgust, and anger, and they have a universal approach that doesn't take into account cultural variations. Now we can get to our first moderately explored function, memory. Brain has multiple different memory functions. For example, you could hit your brain and basically forget all of your past experiences, but you could remember how to ride a bike, how to form a sentence, or some random fact about what is the capital of the country X. The brain manages different forms of memory like semantic memory or episodic memory in different parts of the brain. But these subsystems all work together to encode short-term memory and consolidate long-term memory. In this paper, AI memory is divided into two major categories: short-term working memory and long-term episodic memory. Our best attempt at adding memory to these AI models has been using the context window for short-term working memory, which is really inefficient, and using the model weights for long-term memory. The problem is human memory systems are deeply intertwined with perception, reasoning, planning, and action selection. But working memory in AI, which is the context window, is very limited. For example, a software engineer can manage a project with hundreds of thousands of lines of code without specifically remembering each line. But LLMs don't have the capacity to selectively ignore, forget, and compress data, so they run out of memory really fast. Moreover, humans have multiple layers of encoding and compression to move memory up the hierarchy and form long-term memories, some of it happening while we are sleeping. But AI models have no mechanism for updating their model weights in inference time. There are some promising paths on this issue like subquadratic architectures, which I have a video about in the description. But at the moment, AI agents are very primitive compared to humans in terms of memory formation and gathering experience. Another crucial but moderately explored area is planning. LLMs emulate human planning by leveraging their linguistic knowledge and writing down actionable steps. But in reality, they can't execute even the most straightforward plans because of the following reasons. Gaps in the word knowledge. LLMs lack deep comprehension of word dynamics. It's the equivalent of robots easily running and executing tasks in simulation. But when they are in the real world, they are stiff and slow and very much error prone. Because the simulation can't ever really encapsulate everything that is happening in the word. The holes in the word model hinders AI ability to manage sub-goal interactions and environment changes. And to be clear, we are not talking about robots here. We are using robots in the real world as an analogy. So far, we've been trying to account for this failure by building one very specific workflows that break the bigger goal into simple actionable steps that are also mostly automated. Tools like Na10 or Make.com use this method. But even then, the AI models don't seem to be very reliable. It is strange that models solve very challenging math problems, but can't reliably handle customer support. Another method is dynamic reasoning structures, which is used for agents, like Cursor Code Agent or OpenAI Operator or Anthropic Computer Use. This method uses a combination of reasoning models, probably fine-tuned for a specific task, and a bunch of other algorithmic tools to enhance reliability. But it is fundamentally limited by the AI's ability or the LLM's ability to actually plan and execute. There are a lot of other important moderately explored areas like attention, skill learning, context recognition, decision making, inference time reward mechanism, but it's too much for one video. Now let's get to our first, very important, but rarely explored function, empathy. I know empathy sounds like just kind of a nice to have, but it is actually very fundamental to AGI. Empathy could be interpreted as the ability to deeply understand the internal state of others. It's beyond sympathy, which AI doesn't even have that. Language models try to look empathetic, but in reality, they are unable to deeply understand people's internal state for obvious reasons. As you might have heard, last week OpenAI tried to change ChatGPT's configuration to be a bit more enthusiastic or accommodating, and that was a huge disaster. Part of the problem was that because the AI lacks empathy, they have to preemptively make it to act a certain way, while ideally having empathy and understanding how the person is feeling or thinking right now should determine your approach. Understanding sarcasm is a form of empathy, and these AI models don't seem to get it at all. But even beyond that, empathy is the difference between designing a fantastic product that people love because you deeply understand the user, or building yet another best practice product that is just a copycat. Empathy is the difference between a piece of content or advertisement that resonates with people, or just another boring AI slop. Empathy is the difference between recognizing a unique business opportunity by empathizing with a subset of people, or copying yet another well-established business model. At the moment, it is unclear how can an AI with no internal state, or at least an internal state that resembles humans, can ever develop empathy for us. It might improve as a function of better facial expression or body language processing, but I think that would plateau really fast. Because even humans who have shared experiences have a lot more empathy for each other. And we already share a brain and body structure and a living experience. Finally, I'm gonna give you one more rarely explored and very important area. Then I encourage you to just take a look at the paper yourself. You can just put it inside Notebook LM and ask any questions or listen to a podcast generated for it. Notebook LM is amazing for learning anything these days. Our last rarely explored function is cognitive flexibility. In humans, cognitive flexibility is a higher order cognitive function associated with the frontal lobe. We are able to plan at a high level and focus on finer details. We are able to zoom in on one subtask and quickly load all the relevant information into our working memory. Then, progress or failure, we are able to take a step back and look at the whole picture again. Maybe update the plan and then jump back right into another subtask. Although AI models of today have millions of tokens in their context window, so they are theoretically not forgetting about the bigger plan or finer details. They are heavily reliant on human guidance to understand when to switch between micro and macro. This is very apparent if you ever work with code agents. They don't forget the task, but they might move on from a subtask when it's only half done, or get stuck in one forever. When we jump into the details, we are able to forget about the bigger picture and just focus on the small task. And in turn, when it's done and we zoom out, we abstract all the subtasks away. But the AI is seemingly unable to momentarily forget about one context to focus on another. The solution? If you manually start a chat for the whole plan and each subtask separately, and you move the results in between them, you'll see the AI models are much more capable of handling complexity. And that's basically the state of the art on cognitive flexibility, just doing it yourself. And there is significant room for research. Brain is kind of amazing. We only talked about a small part of what might relate to digital work, but brain also regulates the body, regulates our emotions, controls motor movements, and much more. I'm preparing another video about not the functions, but our understanding of how the brain works compared to AI. It is genuinely bizarre how advanced and complicated the brain is. So if you like to watch that, see you in the next one.